You know, every single time you send a text, stream a show, or even just power up your computer, you're basically commanding this massive army of billions of microscopic switches. So in this explainer, we're going to decode this simple language that they all speak, the fundamental building blocks that, believe it or not, make our entire digital world possible.
It sounds kind of crazy, right? How can all the complexity of modern technology really boil down to something so basic? Okay, so let's dive into this. We're not going to start with the fancy devices we see every day, but with their simplest, most fundamental component. All right, so deep inside your phone, your laptop, pretty much every piece of digital tech you own, there are billions, and I mean billions, of these tiny little units called transistors. Now, for our purposes today, just think of each one as a tiny microscopic light switch. Each one of these billions of switches can only be in one of two states. It's either off or it's on. That's it. To make sense of it all, we represent off with the number 0 and on with the number 1. This simple two-number system is called binary, and it is the absolute foundation. It's the native language of every single computer out there. But see, computers don't just store all those zeros and ones. They need to do something with them. They need to process them. And that's where logic gates come in. You can think of them as tiny little decision makers. They take a look at one or more of those binary inputs, the zeros and ones, and then produce a single yes or no output based on a very specific rule. So how exactly do these little decisions get made? Well, it all starts with three super fundamental gates that really form the basis of almost everything else. So let's meet them: the not, the and the or gates. The simplest one of all is the not gate. It's often called an inverter, which is honestly the perfect name for it. All it does is take a single input, either a 0 or a 1, and it just flips it to the complete opposite. So this little chart here is what we call a truth table, and it shows you every possible thing the gate can do. And the rule is just incredibly simple. If you give the not gate a 0, it spits out a 1. If you give it a 1, it spits out a 0. That is its one and only job, just to invert whatever you give it. Okay, next up is the AND gate. Now, this one's a little bit stricter, and it takes two inputs. You might hear it called logical multiplication, which is really just a handy way to remember its rule, but I like to think of it like a high-security door that needs two separate keys turned at the exact same time for it to open. And if you look at its truth table, you can see exactly how strict this gate is. You've got 4 possible combinations of inputs, right? But only one of them satisfies the AND gate's rule. It's that very last row, where both input A and input B are 1. That's the only time you'll ever get a 1 as the output. Everything else, it's a 0. Now let's meet the OR gate, which is, well, a lot more chill. It also takes 2 inputs, but it's happy to give you a 1 if either input A or input B is a 1. Its rule is just way simpler. It only needs one of its inputs to be on to give you a yes. And you can see the difference so clearly in the OR gate's truth table. The only time it ever outputs a 0 is when both of the inputs are 0. In every single other case, if A is 1, if B is 1, or if they're both 1, the output is a 1. As long as there's at least one on signal coming in, the OR gate is good to go. Okay, so not and or are our basic building blocks. But the real power, the real magic, that all starts when we begin combining these simple gates to create much more complex and efficient tools. So for example, what happens if we take the result from our super strict AND gate and immediately run it through a NOT gate to flip the answer? Well, we actually get a brand new gate called NAND, which is literally just short for not AND. And its behavior is the perfect inverse of the AND gate we just looked at. Remember how the AND gate only gives you a 1 in that one special case? Well, the NAND gate gives you a 0 in only that same case. For everything else, it outputs a 1. And as you can probably guess, we can do the exact same thing with our OR gate. If we take the output from an OR gate and then invert it with a NOT gate, we get another incredibly useful tool. This creates the NOR gate, or not OR, and its behavior is the exact opposite of the OR gate. It will only give you a 1 if and only if all of its inputs are 0. Any other combination and you're getting a 0. So up to now, our gates have been answering questions like, hey, are both inputs on? Or, is at least one of these on? But what if we need to ask a more specific question? Like, are these two inputs different from each other? Now, we could build a fancy circuit to figure this out using the gates we already have. The logic would be something like one of the inputs has to be a 1, but they can't both be 1. It's doable, but it would get a little messy. Thankfully, there is a single gate designed for this exact job.
And this is the XOR gate, which stands for exclusive OR. It just elegantly solves our little problem by outputting a 1 only when the inputs are different from each other. So when one is a 0 and the other is a 1, it exclusively cares about a mismatch.
And its truth table makes this crystal clear. Just look here. When the inputs are the same, either both zeros or both ones, the output is 0. The output is a 1 only in those middle 2 rows, where the inputs are different from one another.
And of course, if we invert the XOR gate, we get its counterpart, the XNOR gate. It does the exact opposite. People often call it the equivalence gate because it's basically a sameness checker. It only outputs a 1 when its 2 inputs are identical. Okay, so we've just met the 7 fundamental logic gates: NOT, AND, OR, NAND, NOR, XOR, and XNOR. We've got these 7 simple little decision makers. But what does all of this add up to? I mean, how do we get from here to watching videos on the internet? Well, here's the crucial point. Individually, these gates are super simple. But by combining billions of them in really ingenious ways, we build incredibly complex circuits. And these circuits, they're what allow a calculator to do math. They're what allow a computer to store a bit of memory. And they are literally the brains inside the microprocessors that power every single piece of digital technology that shapes our world today.
Just think about that. From just 7 basic rules, we have built a world of almost unimaginable complexity and power. It's just a powerful reminder that sometimes the most sophisticated systems can grow from the simplest possible foundations. It really makes you wonder, if this is what we built with the first set of rules, what are we going to build with the next?